Welcome to Civil Engineering Tips channel.
Powerful natural events on our planet, capable of causing significant landscapes and communities. They occur when massive sections of the Earth's crust, known as tectonic plates, shift and grind against each other. This movement releases energy in the form of seismic waves, which travel through the ground and can shake the surface violently. The impact of an earthquake on human structures depends greatly on how buildings are designed and constructed. Well-engineered buildings use flexible materials and reinforced frameworks to absorb and dissipate seismic energy, reducing the risk of collapse. In contrast, poorly designed structures are more vulnerable to damage, putting occupants at greater risk. Understanding both the causes of earthquakes and the principles of resilient building design is crucial for creating safer communities in earthquake-prone areas. Several distinct layers, each with unique properties. At the center lies the dense metallic core, surrounded by the semi-fluid mantle. Above the mantle is the Earth's outermost layer, known as the crust, is not a single unbroken shell, but is instead divided into large sections called tectonic plates. These plates float atop the mantle and are constantly shifting, though usually at rates of just a few centimeters per year. When these plates interact by colliding, pulling apart, or sliding past one another, they can become locked by friction. Over time, stress builds up until it is suddenly released, sending seismic waves through the Earth. This rapid release of energy is what we experience as an earthquake, by the gradual accumulation of stress along fault lines deep within the Earth's crust. As tectonic plates slowly move, friction between rocks along these faults prevents them from sliding past each other easily. Over time, stress builds up as the rocks are forced to bend and deform. Eventually, the stress becomes too great for the friction to hold, and they suddenly slip, releasing a burst of energy in the form of seismic waves. This sudden movement is what we experience as an earthquake. The elastic rebound theory explains this process, describing how rocks on either side of a fault store elastic energy until they abruptly snap back to their original shape, causing the ground to shake. Three main types of seismic waves are generated: P waves, S waves, and surface waves. P waves, or primary waves, travel fastest through the Earth, followed by S waves, or secondary waves, which move more slowly and only through solid materials. Surface waves, however, travel along the Earth's surface and are typically the most destructive. These waves cause intense shaking that can make buildings sway, windows rattle, furniture shift, and even vehicles bounce. The severity of these effects depends on both the magnitude of the earthquake and the distance from its epicenter. Areas closer to the epicenter usually experience stronger and more damaging ground motion. As a result, the impact of an earthquake can vary significantly from one location to another. Shaking in loose, water-saturated soils can dramatically increase the pressure of water between soil particles. This rise in water pressure reduces the friction that normally holds the soil grains together, causing the ground to solid structure and behave more like a liquid. This phenomenon is known as liquefaction. When liquefaction occurs, the ground can no longer support the weight of buildings and other structures. As a result, buildings may tilt, sink, or even collapse, regardless of how well they were constructed. The effects of liquefaction can be sudden and severe, posing significant risks to both property and safety in affected areas. It typically consists of columns, beams, floors, and walls, all together to support and stabilize the structure. During an earthquake, the ground shakes suddenly, but the upper parts of the building tend to stay at rest due to inertia. This resistance to movement causes the structure to experience lateral or side-to-side forces. These lateral loads travel through the frame, putting focus on connections and materials. If the building is not engineered to handle these forces, cracks may form in walls or joints, structural elements can fail, and in severe cases, the entire building may collapse. Proper design and reinforcement are essential to ensure the frame can safely transfer and absorb these earthquake-induced loads, carefully designed by professionals to withstand the forces of an earthquake. They feature strong foundations, reinforced materials, and specific seismic design elements that help them absorb and dissipate energy during ground shaking. In contrast, non-engineered buildings often lack these critical features. Without proper foundations or reinforcement, these structures are much more likely to suffer severe damage or even collapse when an earthquake strikes. The difference in performance is significant. Engineered buildings are far more resilient, protecting both lives and property, while non-engineered buildings remain highly vulnerable to seismic events. Engineers play a crucial role in ensuring the safety of buildings, especially in earthquake-prone areas. They begin by conducting soil tests to determine the ground's safe-bearing capacity, which informs the selection of suitable foundation types. Using advanced software like ETABS, engineers simulate earthquake loads to assess how structures will respond under seismic stress. Accurate sizing of columns and beams, along with meticulous reinforcement detailing, is essential to withstand these forces. Throughout construction, rigorous quality control measures are implemented to ensure that every component meets safety standards. Together, these practices form a comprehensive approach that helps protect lives when earthquakes occur. Buildings with safety in mind is crucial for minimizing earthquake damage and safeguarding lives. Adhering to established building codes and regulations ensures that structures can withstand seismic forces. Consulting licensed engineers during the design and construction process provides expert guidance and helps identify potential risks before they become hazards. Safe construction should be viewed not as an added expense, but as a vital responsibility that protects communities and families. In summary, prioritizing safety in construction is essential for resilience against earthquakes. For more insights and practical advice on engineering best practices, continue exploring resources from the Engineering Tips channel.